Hello everyone, welcome to the lecture 7 of Comsol Multiphysics training course. Today we are going to model a micro-patterned resistive force sensor. So let's begin. So what is resistive force sensor? Basically, resistive force sensor is a general definition when a change in the electrical resistivity occurs by applying a mechanical strain or a stress. Different systems can provide this property. For example, piezoresistive materials are specific materials or semiconductors that change their resistance when a force is applied. And the other type of piezoresistive or basically resistive based sensors are the sensors that their geometry or their structure is changed when the force is applied. And the change of resistance is due to the geometrical and structural changes. For example, strain gauges are one of the most famous type of resistive sensors. The other types are porous structures or fibrous structures that their geometry changes when a force is applied. And finally, micro-pattern structures. This one is the case that we are going to study today. So what is micro-patterning? Micro-patterning or surface texturing means that when we furnish or improve the surface of a material by patterning the surface with microstructures. For example, applying micropyramids, microdomes, micropillars, and so on. These are some examples of applying the micropatterns to a structure. The micropatterning can be done through different methods such as photolithography or soft lithography, laser printing, 3D printing, and so on. It may require specific procedures. There are different examples and applications of micro-patterning and micro-pattern surfaces, such as change of surface area, change of surface adhesion and friction, the fabrication of hydrophobic or oleophobic surfaces to repel water or oil, and so on. So today we are going to model a force sensor based on micro-pattern structure. In fact, the sensor is a thin film where there is two thin layers that are separated by micro patterns. The micro patterns are micropyramids which are placed between the two surfaces, and we have two rigid spacer. In fact, when we apply the force from the top surface, the contact between the top layer and the micro patterns makes the change on the geometry, which eventually changes the resistance. And we are going to see how this force can be measured through the change of resistance of the overall structure. In this study, we are going to discuss contact pairs and contact mechanics, which is very important in Comsol. Also, how to use the segregated solver to separate the steps of solution and global resistance. So let's go to the software. Okay, as usual, we start with the model wizards. And for simplicity, we are going to model the system in 2D, but for sure you can use the same analogy for the 3D design, which is more accurate. So let's start with 2D and then wait to select the physics. In this study, we are going to use the solid mechanics for the contact mechanics features and electric currents for the resistivity and conductivity features, right? After we add the two physics, we continue and we select stationary and done. Now we just wait to go into the software and continue with this modeling and simulations. Now we are in the software, and then first I'm gonna define the force, which is basically we apply that and we see how the force changes the resistance. So let's start with 0 and then we will change it using the parameter sweep as we discussed before. In the geometry, I'm gonna change it to the millimeter because I'm going to make the sensor in the millimeter scale. I'm gonna right click on geometry, rectangle. The bottom, or basically the substrate which holds the micropyramids, has a 12 millimeter width and the height is very small because it's a thin layer, and then we click on build selected. So this is basically the substrate for the micropyramids. To make the micropyramids, we can have different methods. I'm gonna use polygon In fact, when you use the polygon, you add the points to make the polygon. And because here we have a triangle, which is basically the 2D view of a micro pyramid, we are going to use 3 points, right? So based on the geometries that I know, I'm gonna select the numbers of the 3 points of the triangle, and then I will explain these numbers after I created the triangle. So this is the starting point, the next point for X and Y, and finally the last point for the triangle is as this one. Then I clicked on build selected. If I zoom in, this is only one micro pyramid, or in 2D micro triangle, which is placed on top of the substrate, right? The height is 100 micron and the base is 50 micron. This is a random number, so you can change it, or even you can define it as a parameter, and then you can change it for future modelings. But for here, we are going to use only one fixed size, right? Then the next step is to make it multiple units or multiple pyramids. For this, we are going to use the method that we used before. I'm going to go to transforms and then using array. In the array, I'm gonna select this one unit and I'm going to make it in the X direction. So the number I need is 99 and the distance is 0.1. So if I click on build selected, I'm gonna have multiple micro pyramids or micro triangles placed on top of this substrate. It's like you are furnishing the top surface with microstructures, right? The next step is, because these are all same material, to union them into one single geometry or one single domain. To do this, I'm gonna go to Boolean and partitions and then click on union. In the union, because we need all of this, I'm gonna select all by Control A, and then everything is added here, so I don't have to click them one by one. And one thing which is important is to unclick this option, because we don't want to keep interior boundaries. For example, this one is an interior boundary between this triangle and the bottom substrate. I unclick that and then click on build selected. So they are union, right? And they are one material now. Okay, so the next step is to define the spacers between the top and bottom layer. To do that, I'm gonna use a rectangle. The width is 1 millimeter. The height is the same height of the pyramids, so it's 0.1, and the position is at 0, and I have to shift it upward, and then I click on build selected. So this is one spacer and the other spacer is located on the other side, so I'm gonna just duplicate this one, same dimension, and we only have to shift it in the X direction, right? And then build selected. So we have the two spacers. Now we need the top layer. To do this, I'm gonna simply duplicate the bottom one, and we only have to shift it upward for 200 micron, right? So I click on build selected. Okay, so we have formed the shape of our sensor, which is going to be used for further analysis. We can click on form union and build up. The next step, which is very important, and we are doing this for the first time here in this course, is to define contact pairs. In Comsol, when you have the contact between two surfaces or two layers, you have to define a contact pair, which is the two surfaces or two boundaries that are in contact or going to be in contact. For example, in this design, this top boundary is going to be in contact with the outer boundaries of the micropyramids. after we compress it, right? So to do this, we are going to go to definition and then go to pair and then select contact pair. And as you see, we have a source boundary and we have a destination boundary option. Source boundaries is the one that is on top here, and destination boundaries are in the bottom here. But as you see, we have multiple boundaries, which makes it really hard to basically select one by one. This reminds us of using the explicit option. Again, if I want to use explicit, I have to select them one by one. So I'm gonna do a very tricky method, but you can have other methods of selecting if you want and if you know how to use the explicit option. What I'm gonna do is I'm just going back to the top layer and I'm gonna shift it a little bit upward, and then I click on build selected. But don't worry, I'm gonna fix it later. When I go back, I go to explicit and I try to define an explicit. For the explicit, for example, I use down. Down is basically the down contact boundary. Then I switch that to boundary. I click on all boundaries and then I deselect other boundaries except the micropyramids and the bottom layer contact, right? So let me just unclick them and only keep the micro patterns as the selected boundaries, right? So I go to the other side and unclick other boundaries. In fact, we only select the micropyramid outer boundaries, right? So that's it. We have defined one explicit, and we also need to select or define the upper contact surface or contact boundary. So I'm gonna use another explicit, and for this one I use up, and instead of selecting one by one on top, because there is only one boundary, I'm gonna select this one, right? So if I go back and in the rectangle 4 I change the geometry, the original position, then build selected, what happens is the geometry shifts backward to this original position. But if I go to the up and wait, I will see that we have multiple sections, which makes it easier instead of selecting them one by one, right? So we are good. Then we go to contact pair. In the source boundary, I'm gonna use up. So again, I'm gonna use this drop down menu, and the up and down automatically appear here. So I select up, then I activate destination boundary and then use down. So we already defined the contact pair, which is very important, and we are doing that for the first time here. Again, this is necessary when we are going to have contact between two different objects or domains, right? So we are good with the geometry. We are going to go to material. What I'm gonna define for the materials are just blank material. I'm gonna define the spacer first. For the spacer, I'm going to define very rigid or stiff material because we don't want to have deflection on these two spacers under the force. So here for the Young modulus, I'm gonna use a large number, for example 100 gigapascal. For the Poisson ratio, I just used 0.2. For the density, I can have a number like 1500. The electrical conductivity, we want to have a very small number. In fact, it acts like an insulator because we don't want to have a short circuit through the top and bottom. So we have 1e minus 14. And for epsilon or relative permittivity, I just use a number like 2. The reason that I used a small number is if you use 0 here, you may get some errors. So even a small conductivity is fine to make it as an insulator. I mean a very small number, right? The next step is to define the material for our flexible or elastic contact layers. Again, I'm gonna use a blank material and select top and bottom, right? So I selected the two domains which are going to be in contact, and we suppose that because of the force there are some sort of flexibility which causes more contact. So the more force, the more contact between the two layers, which changes the resistance of the system. So this is how the sensor with microstructure works. And then in the Young modulus, as I said, I'm gonna use a relatively elastic material. So I'm gonna use 2E7, right? And for the Poisson ratio 0.4, it mimics some sort of relatively flexible polymer, but in fact it's not one single polymer. It has to have some conductivity so that when we change the geometry because of the force or the contact, we change the resistance, right? So for the density, I'm gonna use 1200. For the electrical conductivity, I'm gonna just use like 2 Siemens per meter, and the relative permittivity of 2. So it mimics, for example, a polymer composite which has some conductivity because of adding some conductive fillers. In reality, for example, you can combine some conductive powders like carbon-based powders into a plastic or so, and then shape this geometry. So we have some sort of conductivity and flexibility in the system, right? In the solid mechanics, I'm gonna change the out of plane thickness. Here, I'm gonna just use 1 millimeter. But again, in reality, when you have a 3D design, you can make it more accurate using the 3D design. And same thing with the electric currents. I'm gonna change the out of plane to 1 millimeter. So let's go back to the solid mechanics and define the boundary condition. So as you remember, we are going to see how the force applied from the top layer will change the resistance. So I right click and then I use a fixed boundary condition, and I'm gonna fix the bottom surface, which means that the system is fixed from the bottom, right? And the other boundary condition is the boundary load, which is the force that we are going to monitor. The force is applied to the top layer or the top surface, and the type of force we are going to use the total force, and the amount is in the y direction, which is minus f, right? F is 0, but in the future we are going to use the parameter sweep to change it, right? I think that's it. The last boundary condition, which is very important, is the contact. We have to go to pairs and then define a contact pair. There should be a contact pair defined when we have such problems, that the contact will occur on the system, and the contact could be different. It is very important to define it properly. After we add contact here, we click on this add, and it is already there because we already defined it in previous steps. So I click on contact pair 1 and OK. To remember what it was, let me just remove it again. Go back here in the contact pair we defined. I'm gonna use another name. For example, we can call it contact 1, and then we go back to our contact, and then plus we have contact 1. Now you understand what we added here. That's it. We are done, and then we are going to the electric currents. So in the electric currents, we are going to add a ground as a reference, which is always we have in our system. So again, I'm going to use the bottom layer or bottom surface, and the other one is to apply a terminal. As you remember from our lecture on electric currents, we need to use a terminal to find the overall resistance of the system. Okay, and because we are going to measure resistance, we are using current. If we deal with conductance, we can use voltage, which basically not a big difference because conductance and resistance are inversely related, right? So I click on current and I imagine that the current is applied through the outer surface of the top layer, right? And the amount, we can use a value of, for example, 1 milliamps, right? That's it. So we are good and everything is set with the electric currents physics. So as you remember, when we combine two physics, we may have a multi-physics added in the system. But here, we don't have it. Or in fact, the Comsol does not automatically combine electric currents and solid mechanics. But don't worry, we are going to deal with this issue and we try to solve it in such a way that it gives us the results, right? Okay, let's go to mesh, and in a mesh, I'm gonna switch to extremely fine and then click on build all. So we are good with the mesh, and the last step is study. Here we are going to change the study options so that we fix the issue with combining electric currents and solid mechanics, because as you see, there is no multi-physics added here. To do this, let's click on the stationary and then click on get initial value for steps. In fact, it solves the problem when everything is at the initial values or initial conditions, which is 0 here, right? Okay, so as you see, everything is 0. The results are stress, contact, and electric potential. The electric potential is from the electric currents and the stress is from the solid mechanics, right? So after we have this, we can modify our solver configuration. The reason that I use the get initial values or get initial value for step is to modify the solver configurations. When I do that, I can open this drop-down menu under solution, and this is the stationary solver, which is important. I'm gonna discuss this option in other examples as well. If I open the stationary solver, I see I have a fully coupled option here in the steps of solving. The fully coupled option solves all the variables or the dependent variables of the physics together. And for this case, because they are not combined in multi-physics, using this option will not give us the results of the electric potential. And you always get the 0 value for the electric potential. You can give it a try if you want. How to resolve this issue is to add a segregated solver. As it sounds, the segregated solver can separate the solutions or do it step by step. So I'm gonna add segregated, and if I open it and click on segregated steps, you see I have all the dependent variables in one window. What I need to do, I have to add a segregated step and then go back to the step 1, and here remove the electrical component, which is going to be done here. So I only keep the displacement field, which is the dependent variable from the solid mechanics. Then I go to the segregated step 1 here, and then I add them separately. So let me add electric potential and terminal voltage. So in fact, I separated the dependent variables of the two physics. In a simple word, we can say that it solves for the solid mechanics and then solves for the electric potential, which is kind of true. For example, you get some deformation and then the electric potential is calculated. Something like that. I just explained it in the simple word. Okay, I think we are set with this. We have to go back to the stationary and then go to the study extension, because we are going to define an auxiliary sweep on the force, right? I click on add, I have the force. Here, I'm gonna change the force from 0 to 1 Newton, or in fact, we are going to see how changing the force from 0 to 1 Newton will change the resistance. This is very important in the design of a sensor. In fact, we can design a sensor based on that, and from the resistance results in the experiments, we can know how much force is generated, right? So I'm gonna use 0.1 as the interval and 1. So this is the force in Newton because I used total force in the boundary load here, right? And it is minus, which means it is downward as a compression to our sensor, right? So we are set, and then the last step is to solve. So I'm gonna click on compute and wait for solving. Again, it may take a while to solve for this parameter sweep. I should mention that here we don't have any time variable or something changing with time, but you can also apply this force as a function of time so that you can capture the effect of the rate of force or the speed of changing force, right? But for now, let's just wait. Okay, the problem is now solved, so let's dig into the results and see what has happened. Okay, as you see, we have the stress results from the solid mechanics and electric potential from the electric currents. If I move forward and let me change the force to 0 and then plot, so you see there is no stress or deformation on the system, and as we increase the force, I'm gonna get some sort of deformation and a stress, and the more force, the more deformation. And finally, if I go to some numbers like 0.9, I get more deformation, and 1, which is the max. So it means that when we apply force, we get some deformation on the contact area in the micro scale. That's the interesting part of using micro structures or micro pyramids in this case, right? It can capture the effect of changing the force in the small scale. Once again, you can see the deformed micro pyramids. In this example, we just used a very simple material, but we had the cases that we're dealing with more different types of materials like soft materials, hyperelastic materials. You can also try those types of materials and see how you get more deflection, right? But the aim of this lecture was to show how the force can change the resistance as a resistive sensor. Okay, so we are good, and we got the force applied and the change on the geometry, which eventually changed the overall resistance of the system. Let's see how it will change that. Okay, to do this, we can get both the numbers and the graph. For the numbers, we can just go to derived value and again global evaluation, and then under expression, under electric currents, because it's an electrical parameter, and terminal, we can get resistance. Double click and evaluate. So it gives us a table with the amount of force and the amount of resistance, right? So if I want to show that in a graph, I just go to the 1D plot group. Under that, I'm gonna right click and say global, and on the y-axis data, in fact the x-axis data is the force. I already have the resistance, but you can again find it under electric currents and terminal. So that's it. I click on plot and I see the change of resistance under the force. So you see we have the resistance decrease as the force is applied because you have more contact area and more electrical junction from the electrical point of view, right? Okay, this is very interesting. In fact, you could monitor the effect of the change of force and the resistance. And it is not a very practical case. We just want to show you how to model a microstructure and a force sensor based on the resistance change of the overall system. I hope you enjoyed this video, so stay tuned for the next videos.